In physics, this is called the orthogonality relation, and this is called completeness in mathematics. So there you have it, your full quantum mechanical wave function, where CNs are obtained here. Hi guys, so welcome back to another video. This is when I'm shooting this video, this is a weekend, so hopefully you guys are having a nice one. So let's get back. Actually, this is lecture 7, but this is an extension of lecture 6. The reason being that there were a couple of things that we ought to do more that we didn't do in lecture 6. The link to this lecture, the last lecture, would be in the description box. So if you guys are here in this particular video for the first time, it might pay to watch the last lecture first and then continue with this one. So in the last lecture, we ended sort of here. We had figured out our wave function, time independent wave function, with n equal to 1, 2, 3, etc. I'll also sometimes denote them by natural numbers in this manner. N equal to 0 is no good, first and foremost, as you see, because this term then would simply be 0, right? So yeah, so n equal to 0 doesn't make too much sense. The wave function would completely collapse. But for higher higher integral values of n, these are the correct wave functions. And the goal today, so what is it that I want to do? Well, the goal is I want to actually evaluate the full wave function, which is, we know from previous lectures, it's a function of both x and t. Then you would have some undetermined coefficients which we need to figure out. Then you have this psi n of x, which is this guy here. So this part we have done. And you would have some phase factor, e to the power minus I by h cut E n of t. Recall that this part we figured out from the method of separation of variables, right? This was the easy part, figuring out the phase. We did this in lecture 5, if I'm not too wrong. So let me just quickly go back and see. That is right. So we had defined, for example, if you go back to lecture 5, again it would be in the playlist, you see that we have figured out the phase first, because that was the easier thing to figure out, and later in the last lecture we had figured out this guy. So now we just want to figure out the full wave function, which would be a superposition of these guys. But before doing that, I want to highlight a couple of properties of these wave functions, which would be sort of quite nice to first visualize. So imagine you have this graph. So this is the x direction. Imagine this is where your x equal to a is, and this is 0, of course. And you want to plot, say, your psi n of x. So the first one, for n equal to 1, this is simply a sinusoidal function, right? What about the second one, n equal to 2? So this is, say, n equal to 1. What about n equal to 2? Well, if you plot, you will see that it's somewhat like this, n equal to 2. Let me color them. Color. For example, for n equal to 3, you would have something like this is n equal to 3, and so on and so forth. So the point being, as you go higher up in n, the number of zero crossings increase by 1. What do I mean by zero crossings? Well, these are zero crossings for you: this point, this point, this point, etc. So for example, n equal to 1 had no zero crossing. It did not touch the x equal to 0 line, and that we know because that's how the sign behaves in the first quadrant. Then you had n equal to 2 function, which was this middle function, and you see this has 0 crossing once. N equal to 3 has 0 crossings in a couple of places. Sorry, and this feature would persist for all psi n. Okay. The next thing that I want to talk about is called the orthogonality. First, let's talk about orthogonality first. Well, from high school physics, we know what orthogonals are. So this is one line, this is the other line, right? So these are orthogonals. For example, if I'm in orthogonal lines or rays. In this functional analysis business, orthogonality means infinity to infinity psi m star x psi n x is equal to 0 for m not equal to n. A bit of notation. This is, in mathematics, this is called for. Do you see why this can sort of be related? This can be the nomenclature sort of hints that this is a good definition. It tells you that this one guy psi n, for example, has nothing to do with psi m. It's completely in the orthogonal direction, right? This you might think from vector analysis. If you have a vector a in this direction and a vector b, for example, in this direction, which is orthogonal, then you know that a dot b vector is 0, right? This is exactly this is just the functional analysis version. This is just the functional analysis version of the same equation. So this dot product gets replaced by this integration here because this is a function. You have an extra complex conjugation because sometimes these can be complex. It's not necessary that they are real, but in this particular case, of course, we have them real. So in this case, of course, the start doesn't make too much sense, but yeah. And this is quite immediate to follow, because if you perform this integration 2 by a 0 to a dx sine m pi a x sine n pi a x, you'll see that this is 0. Actually, of course, if the right hand side is 0, you don't need this guy. This is just a normalization. You might forget about it. For all m not equal to n, you can simply verify it by integration. Of course, mn are natural numbers. right? So you see that this is the same formula that I wrote here. This is the same formula. Oops, I missed a dx. You see this is the same formula, right? So we have figured out what the psi's are. So this is psi n, this is psi m star. Of course this is real, so m doesn't make too much sense. And this was the root 2 by a normalization. This was this root 2 by a normalization. So there are two of them, that's why you have 2 by a. Okay, so this was the first thing. The second thing that I wanted to talk about, point 2. Actually, before that, let me ask you this. Let's figure this out. What if m is equal to n? Well, you see that then this integration is actually not 0. Square, because you have the same guy here for m equal to n. You will see that this is actually not 0. This is 1. And this normalization then becomes sort of important. It's with this normalization that you get 1 here. In maths, so this is really written in a succinct way. This tells you psi m star x psi n x delta mn. In physics, this is called the orthogonality relation. Orthogonality. This delta x that I introduced here, for those who are unaware of it, it's called Kronecker delta. And this is a symbol actually. So what does this symbol mean? This symbol means delta mn is 1 or 0 if m equal to n, otherwise. This is the definition of Kronecker delta. So this is called in physics a Kronecker delta. Okay, so we arrive at the celebrated relation that we'll see over and over again in actually all of physics and maths, that they are orthogonal to each other. This relation. Of course, depending on what size you get, on what space you are having your quantum mechanics, this variables here, this a to b, for example, if you have, it would be different, right? Okay. So the second thing that I wanted to show is called completeness. And completeness, by definition, in maths, means that you can have any arbitrary function fx, for example, arbitrary. This is arbitrary. Arbitrary, except the fact that it can at best have a finite number of discontinuities, finite number of finite discontinuities. It cannot have infinite discontinuities. The definition of completeness is that it can be, for some Cn, this function, can be written as a linear superposition in this manner. And this is the definition of completeness. That if you give me any function, arbitrary function, with the constraint that it can at best have a finite number of finite discontinuities. Of course, if it doesn't have discontinuities, all the better. So this function can be expressed as a sum in this manner. So this is called actually, if these are sine functions, or cos or sine, or for example exponential functions, then this series is called the Fourier series. In physics, this series is called, in physics and maths, this series is called the Fourier series. If your psi n's here are either the sine, cos, sine, cosine functions, or the exponential functions. Okay, and this constraint, that this condition that I highlighted here, this is called the Dirichlet condition. Okay, great. So how do I figure out? Of course, then the point is to figure out these Cn's, right? So I know what these phi n's are. In my case, these are the sine functions that I derived before. Somebody gave me this fx to expand in this basis of science. So basically the task is to figure out these Cn's, right? And it's almost immediate, right? Because assume that your fx is Cn and 1 to infinity, Cn psi n of x, which we know are simple sine functions. Something like this. Then using this formula that we just derived, using this formula, sorry, in our case this was from 0 to a. In this particular case, you immediately see that if I were to multiply this fx, chosen fx, with a particular, say, sine pi m pi ax, and then integrate from 0 to a, what do I get? I get this simple expression equal to 1 to infinity Cn integral dx sine pi n pi ax. This is this guy times sine pi m by ax. So which is this guy, right? Aha. And then you can immediately use this formula, which tells you that this actually, this expression is a Kronecker delta. So this Kronecker is Kronecker delta. But I already told you what Kronecker delta is, right? So Kronecker delta is 0 unless n is equal to m. So when you take this sum only the Cm survives, right? So this is Cm. Do you see this? Because for in the sum for every n other than n equal to m, this is actually 0, and this is the use for Kronecker delta. So this gives you Cm. So you have figured out what Cm is. So Cm, so Cm is simply Tx psi x star. Well, this star is a bit superfluous in our case because everything is real. So psi x star is psi x, but this is the general formula. And you can have fx as with these Cm's, and this is called completeness in mathematics. Okay, great. So, and the final thing that we need to do to figure out the full partition function, this is the last thing that we need to do, is 3. Recall that the full wave function, the time dependent wave function, was a sum of some constants Tn. Should I write Cn? You guys tell me. So this, let me write Cn psi n of x times e to the power minus I by h cross En times t. This Cn has nothing to do with this Cn here. Different Cn, right? Different Cn. So please don't confuse the Cn that we have. It's just, I could have called it C prime n or something, or Dn, or anything. Just, it's customary to call these coefficients C, so I'm using C, okay? Okay, so how do I figure this out? Well, let me also write the expression for En that we have found out in the last class. So your En actually is n square pi square by 2m a square. This was last lecture. So if you guys are joining for the first time, kindly take a look at that. So again, the only goal now is to what I want to do. So the only goal is to figure what these Cn's are out, right? Okay, so this is again, so now I think you can sort of guess where I'm headed. So this capital psi x of 0, this psi with t equal to 0, so that I can just get rid of this part, unnecessary that is. So this reduces to Cn psi n of x, right? From this part, from this equation, the t part just disappears because I am figuring out psi n. And if you followed the previous calculation, this Cn from using the orthogonality of the sine functions, can you guess what this would be? This simply would be Tx capital psi x0 times sine n pi y a x, right? Do you get this? Because I did it a bit quickly. So you see this guy has a sign here, because these capital small size are actually signs for me, and again I multiplied it with another sign, and then I took the integration. So the sign here and the sign here gives me a Dirac delta function, which means the only surviving element from the Dirac delta function, this the Cn, would be the same n as here. This is exactly, for example, what we did here. Exactly analogous, right? That's why sort of I derived it first for you. Okay, so let me write it here. Let me also write what these ENs are, or maybe actually. So the point being that now someone has to tell me this is an input, extra input from outside. The maths doesn't tell you what the wave function is at time equal to time t is equal to 0. This needs to be say given by the experimentalist or whatever from outside. It cannot be derived from math. This is like the boundary condition or the initial data. These are called initial data, because this specifies the state at t equal to 0, right? With this, if someone gives me this, then I know the full partition function. Sorry, not the partition function. I know the full quantum wave function, which is given by this guy. Copy. Let me paste it here. And let me make this a bit neater. Let me put this here. So, and put this here. So now I have solved for everything with Cn given in equation 1, this Cn in equation 1, which of course, again to highlight, depends on the initial wave function. I now know the full quantum mechanical wave function, where with the energies are given in this manner with n. So there you have it, your full quantum mechanical wave function, where Cn's are obtained here. This is your Cn, and this is the energy has already been also figured out. So this is your energy here. Given an initial wave function, this expression determines the full quantum mechanical wave function for you. Okay, I think that's all I wanted to discuss today. Hope this was helpful. If this is helpful, you know what to do. Kindly subscribe and share it with your friends and like this video. See you in the next one.